Okay, so last time we were talking about independent random variables, and I made the point that if so, in terms of the joint distribution, if x and y are independent random variables on the same space, then the CDF will be a product of the marginals. Okay. In particular, if x and y are discrete, then the PMFs will be a product, and if they are continuous, then the PDFs will be of the product. Okay, so and I sort of explained how one could read off independence of random variables by looking at the table uh, and the marginals. So what it was that each value in the table should be a product of the corresponding margin. So you see that kind of interpretation shows you that there's something special about independence. Okay, so one quick generalization of this will be for functions of random vectors. So I'll leave this as an exercise. I mean, it's straightforward. If x and y are independent, and g and h are functions from R to R, then the expectation of g of x, h of y is the product of their expectation. So expectation of g of x times expectation of h of x. So this says that if x and y are independent, then their functions, the expectation of their functions also factor. Of course, you should be careful not to take a function which involves both x and y. So g is a function purely of x and h is a function purely of y. Then the expectation of their products is the product of their expectation. Okay. So this again you can do in the discrete and continuous cases separately, and you will see that this happens in either case, and this is primarily because of this factorization that I mentioned. Okay. So far we have been talking about two random variables and their independence. So let's see what it means for a general family to be independent, general random vector. So a family x1, x2, etc. It need not even be finite, but it's countable of random variables is said to be independent if the events xi less than or equal to xi for I in some subset j are independent for all finite subsets j and all possible small x1, these are small x2 etc. up to small x of the cardinality of j. So if you remember, for two random variables we said that these two events x less than or equal to a, y less than or equal to b should be independent for all a and b in R. So now with the generalization is you take any finite subset of the indices and you take any collection of real numbers, then these events should be independent. Okay. And independence of events of more than two events we have already discussed. This is this is already quite complicated. I mean, it's not just that you take pairs, right? So remember we discussed the notion of pairwise independence and the difference between independence and pairwise. So these are very, very stringent conditions. So if this family is independent, then something nice is going on. Okay, something tractable is going on that one can hope to analyze. Okay. Okay. Right. Okay. So, for example, if you have n many coin tosses, all independent, I mean, when you sort of think that they are independent, and that will be verified by such a condition. So, okay, maybe I'll just write that explicitly. So, n coin tosses, then you don't tend to think or n die throws, let's just say, and xi is the outcome of the ith die. So there's no reason to suspect that one throw depends on the other. So that's the kind of assumption that one takes. Okay. All right. So now I'm going to change topics. So are there any questions about independence? This independence is a very important theme, and we'll keep coming back to it. Okay. So we will revisit this. Yeah. But if there are any immediate questions, you can. Okay, so I'm going on to a new topic, and that's covariance. Okay, so let me remind you let me go back to the fourth lecture. So we were talking about paired data sets, right? So we had, I gave this example of heights and weights of students in this class. I mean, that's some data set. So in general, you'll have some xi, yi, and you can visualize this as a scatter plot, but you want to know how they are related. I mean, there might not be an explicit relationship, but there might be some kind of correspondence. So you do higher and lower values of x correspond to higher and lower values of y. Okay, or the other way around. And so we saw this in terms of something called the sample correlation coefficient. Okay, so this was at the level of data, and now we want to make a rigorous mathematical framework for this, and this starts with covariance. It's not exactly covariance, but we are getting there. So let me define what covariance means. So the covariance, so it's related to variance, as you can see, covariance of a pair of random variables x and y on a common probability space is, we'll write it as cov of xy, and this is the expectation of x minus expectation of x times y minus expectation. So if you remember the formula for variance, the variance of x was expectation of x minus expectation of x whole squared. So here, instead of having whole squared, we have x minus expectation of x, one of the factors, and the other factor is now y minus expectation. So in that sense, it's a bit similar, except that it now involves two random variables. Okay, and here is a remark maybe. So let's expand this. So cov of xy. As I said before, don't get confused that there's expectation of expectation. I mean, if you want, think of expectation as something new, and expectation of y as something new, and then you use linearity. So we'll do this directly. So let's expand this out. So I have xy minus x times expectation y minus y times expectation of x plus expectation of x expectation. Okay, and so this is expectation of xy. Expectation of y is a number. I pull it outside, then I get expectation of x. Similarly, expectation of x is a number, then I get expectation of y plus expectation of x, expectation of y are numbers. Again, same thing. This is the factor times expectation of 1. Give myself some room. Okay. And now you see expectation of 1 is 1. And so these two terms cancel. And so I get expectation of xy minus expectation of x times expectation. Okay, so this is the easier way of calculating. Okay. So let's build some intuition about why this is the right thing to do. So examples. So suppose x and y are indicator random variables. So you remember what that means. So let's say x is the indicator of A and y is indicator of B. So A and B are events, some events. So indicator random variable means that x is 1 if A occurs and 0 if A doesn't. And similarly, y is 1 when B occurs and 0 if it doesn't. Okay, so let's compute cov of xy, the covariance. Now I'll use this formula. This is expectation of xy minus expectation x, expectation of y. But you remember what we said about expectation of indicators. What is it? Oh, sorry. What is the expectation of an indicator random variable?
So the probability of A.
That's it. So expectation of x is probability of A. And expectation of y, there by a similar argument, is probability of B. And what is expectation of xy?
Probability of AB.
Right. So this is because if you write out the formula for expectation, you will only get a contribution when x is 1 and y is 1. Okay. So this can be written as probability of A intersection B minus the same thing. But I will, so okay, so that's one way of writing it. I will write it in another way. So this is the probability of x equal to 1 and y equal to 1 minus the probability of x equal to 1 times the probability of y equal to 1. So if you want, I'm going a step back. Okay. This expectation xy will only get a contribution from here because this will be 1 times this, other terms will have a 0. Okay, so let's stare at this formula. Now suppose cov of xy is greater than 0 and assume A and B are not null events. In other words, probability of A and probability of B are not 0. Okay. Okay. So that means, so if cov is positive, That means, or it's if and only if probability of x equal to 1 and y equal to 1 divided by the probability of x equal to 1 is strictly greater than the probability of y equal to 1. Right? So this guy is positive. I've just switched sides and divided by this. This is not a problem because a and b are not. What is this though? What is this quantity? How can we re-express this quantity?
Probability of
Yes?
Y
x.
given y given
Uh,
x.
say that again, Kunal.
Probability of y given x.
Y given x what?
Yeah, equal to 1.
Okay, you have, yeah, probability of y equal to 1
Y equal
given
to 1, give x equal to 1.
that. Yeah. Not, so you have to be precise, by the way. I mean, if you'll write probability, if you say this is equal to probability of y given x in an exam, you will certainly lose marks. Okay, you have to be, and you don't write an equal to 1 somewhere. Okay, so probability of y given x equal to 1 is greater than probability of y equal to 1. Right? So what does this mean? So what's the moral?
That the occurrence of x is affecting the occurrence of y.
Yes, but more something stronger. X equal to 1 makes it more likely. Not only does it affect, it makes it more likely that y equal to 1. Right? So given x equal to 1, the probability of y equals 1 is more than the probability of y equal to 1. So therefore, and a similar calculation will show you the other way around also. I mean, I just divide, I switch x and y for example. Okay? And therefore, x and y are positively correlated. Or in this case, A and B are positively correlated. So A occurring makes it more likely that B occurs. Okay? And similarly, and by the same argument, if x is 0, I mean,
Then independent.
so they're not A not occurring will is makes it more likely for B not to occur. Okay? So in general, so this gives the intuition. I mean, this is just for very specific kind of random variables, which are these indicators. But in general, the intuition is that x increasing corresponds to y increasing. And x decreasing corresponds to y. Okay, so if we go back to the scatter plot, it would say that there's a kind of drift in that direction. The points tend to sort of align in some kind of not necessarily a line, of course, but in this general, they'll be in some tube in this oriented that. Okay, that's the idea. Okay, and similarly, if curve is negative. So x, in that case, x increasing would correspond to y decreasing in that way. Okay. So let's do an example. Okay. So suppose the joint density of the random vector xy is fxy. I'll skip the subscripts. This is 1 by y e to the minus y plus x by y, if x and y are positive and 0 otherwise. Okay. So first of all, check that this is a valid PDF. Okay, so which means what? You have to integrate this with respect to x and y and get 1. All right. So let's find cov of x. Okay. So first, so we'll use this simpler formula. This one, expectation xy. So we have to calculate 3 quantities: expectation of xy, expectation of x, expectation. Okay. So let's do this one. Okay. So let's do expectation of y first. So right. So what do we do? So we integrate this density with respect to y. Okay. So we have integral 0 to infinity y times. Okay. So let me write it. Let me write integral 0 to infinity dy, 0 to infinity dx. It's 0 to infinity because x and y is positive. So I have 1. Okay, so I'm integrating y and I have my density 1 by y e to the minus y plus x by y. Okay, and you can see that the y's cancel. Okay, and so I'm going to get integral 0 to infinity dy. Let me take the things that do not depend on x here. So I have e to the minus y, and then I have integral 0 to infinity dx e to the minus x by y. Okay, and what is this now? What is the, so you guys are much more familiar with such integrals, so you tell me, what is this? What is this integral? Yes?
So minus y into e raised to minus x by.
No, this is something, I mean, this is a definite integral, right? So you have to tell me what the answer is. It can only depend on y.
It's y, sir. It's y.
That's right. So it's y. This is a standard exponential integral. You think of y as a constant and you integrate with respect to x. And now what is this integral? Again, this is something that you would have seen. This you can, I'm not going to do the integral. This is using integration by parts, you can get it. Anybody? You've forgotten all your integrals, but I'll leave you to check that this is one. Okay, so now so that's one down, 2 to go. So let's now do integration expectation of x. So again, this is 0 to infinity dy, integral 0 to infinity dx. Now I have x times 1 by y e to the 1 by y e to the minus y plus x by y. Okay, so right. So now this seems a little harder. Okay, so now I take y e to the minus y dy over here, and then I have integral 0 to infinity dx x e to the minus x by y. And again, I leave it to you to show that. Oh, sorry, what did I do? This is 1 by y. So 0 to infinity 1 by y e to the minus y dy. And this is the same kind of integral as this. but there's this extra y, and you will see that you get a y squared. And so one of the y's will cancel. So you again get y e to the minus y dy. Oops. And so this is y. This is the same integral. Okay, lastly, expectation of xy. So 0 to infinity dy, 0 to infinity dx. Now I have xy times 1 by y e to the minus y plus x by y. So 1 y cancels. And so this is, now I again take dy, and I'll take the factor of e to the minus y over here, and I have integral 0 to infinity x dx x e to the minus x by y. This is exactly the same integral as here, so you get y squared. So this is integral 0 to infinity dy e to the minus y times y squared. So what is this integral? This will turn out to be 2. Do you remember what the formula is in general for integral 0 to infinity dy e to the minus y to the n? Do you know what this integral is called? If you know what it's called, you should be able to tell me the answer.
No, sir.
Okay, so nobody seems to know. So this is called the gamma integral. And the reason it's called the gamma integral is because this is equal to n minus 1. So I could have tricked you and tried to ask you what is y cubed, and I would have said it's 3, but it's not, it's 6. Oh, sorry. Yeah. What am I saying? Just a second. Maybe it's n.
No, sir. Yeah, this is n factorial.
N
It is gamma of n minus 1. Or
Gamma of n
gamma of
plus-
n plus 1.
That's right.
Yes,
Gamma.
sir. Right.
Cannot draw straight lines. All right. Okay, so we are done. So now, so curve of xy is therefore 2 minus 1 times 1, which is 1. Okay. So yeah, so I mean such integrals I can ask you to evaluate. So you have already seen this in your 101 course. So I mean it's not unfair for me to ask you to compute expectations or covariances which involve or variances which involve integrals like this. I mean then you cannot complain that this is too hard or whatever. I mean this is something that you should be able to do. Okay. Any questions about this example? So please make sure that you are able to evaluate integrals like this. I mean, as I said, this is integration by parts, and this is y squared integral, or this is y integral. Hold on. This is again the same integration by parts. You get y squared because there's extra change of variables gives you y. Okay. Right. Okay. Very good. So if there are no more questions, no further questions, let me go on to properties of covariance. So the covariance is a very important measure of the relationship between two random variables. Okay, so one has various properties which is important to know. Okay, so the first is I already hinted towards this. What is covariance of xx? If I take y equal to x, what will I get?
This is the variance of the distribution.
That's it. So this will be variance of x, not of the distribution of the random variable. This is just from the formula because, as I said, if I take y equal to x, I'll get expectation of x minus expectation of x whole square, which is precisely the way. Okay. This is just from the definition. Okay. The second thing is that covariance is a symmetric property. So covariance of xy is covariance of yx. This is again clear from the definition. Right? So multiplication is symmetric. Okay. So these are kind of easy properties. Now let's go to something maybe a little more interesting. So let me take, okay, so let C be a real number. Then covariance of Cx and y is what? So what's going to happen if you replace x by Cx? So you'll get a Cx over here and you'll get expectation of Cx. But expectation of Cx, we have seen by linearity of expectation, is C times expectation of x. So I'll get C outside, I'll get C times the same thing, and this of course is unchanged. And again, using linearity of expectation, I'll pull the C outside. Right? So this is C times covariance of x. In particular, so a consequence of this, and therefore, if I want to calculate variance of Cx, this is covariance of Cx right, by property 1, and therefore I take a C out from here. Okay, I can use all properties here. So by 1, this is C times covariance of x Cx by 3, which is C times covariance of Cxx by 2, which is C squared times covariance of xx by 3 again, which is C squared times variance of x by 1. So the variance of constant times a random variable is not the constant times the random variable. Right? I mean that's not going to be correct, because if you think dimensionally, variance is like squared. Right? So it will pull out a factor of square, and therefore the standard deviation of Cx is C times the standard deviation of x. I have not introduced notation for this. Okay. Yeah, yeah, okay. Is this okay? Everybody is okay with this? Actually, this is wrong. I was hoping someone, I think most of you are either not there or sleeping or whatever. This cannot be C times, because the standard deviation is always positive. If I take minus x, I should not get minus 1 times the standard deviation. So here it should be mod C. Absolute values. So that was not quite correct. All right. Yeah, so Soham asks in the chat if its covariance is similar to an inner product, and yes, it is similar to an inner product in an appropriate space. But I'm not going to get into that. But yes, there is it's natural to think that way. I mean, because the variance is positive, and so you have also proportion. I mean, this constant will come out. So it's natural to think in terms of inner product, and that is correct. That intuition is correct. And the next property further solidifies this view. So what is covariance of x times y plus z? This this is equal to covariance of xy plus covariance of xz. So again, linearity, and this or if you like, distributivity. So you know, this this further solidifies the view that it's like an inner product. And again, this you can, you know, if you just expand this out, I mean, if you replace y by y plus z and open up the brackets, you will see this immediately. Okay, so if you are not following this, please do the exercise. I mean, do the computation. It's easy. So since expectation of x times y plus z is expectation of xy plus expectation. Okay, this is an important property because this allows us to look at covariance of sums of random variables. So suppose x1 up to xn and y1 up to ym this way is a random vector, therefore it's a common probability space. Then cov of sigma I equal to 1 to n xi, sigma j equal to 1 to m yj is what? I mean, by this property you can sum these things up separately and use property 2, whatever. So I have I equal to 1 to, sorry, n, j equal to 1 to m, covariance of xi yj. Okay. So so you simply take all possible cross covariances between all the xi's and all the yj's, and you sum all of them up. Okay. So in particular, we can use this to compute this variance of a sum. Variance of sigma I equals 1 to n xi is covariance of the same object twice. So I equal to 1 to n xi, j equals 1 to n xj, right? Same things. I just I didn't put I here because we need 2 indices. They're dummy variables anyway. Okay, now what's going to happen? So there are 2 kinds of terms. There are terms when I is equal to j and terms when I is not equal to j. So let's split this up. So let's write the sum I equals 1 to n of covariance xi plus sum I less than j, 1 less than equal to I less than j less than equal to n of covariance xi. Is this correct?
So it should be twice of the covariance of x.
That's right. So good. So you get a covariance xi xj when you take the ith term here and the jth term here, but you also get it when you take the jth term here and the ith term here. Okay. I mean, for example, x2 x3, covariance of x2 x3 will come from x2 here and x3 here and x3 here and x2 here, and both are the same from by property 2. Okay, and what about this? What is this guy? So this as we have just seen, covariance of is of the form covariance xx. So this is the variance of xi plus twice the same. 1 less than equal to I less than j less than equal to n, covariance xi. Okay, so this is an important formula. So I'll stop it. Okay. So this tells you how to compute the variance of a sum. So it's the variance of a sum is not the sum of the variances. So no linearity of variance. Linearity of expectation, but no linearity of variance in general. You have to consider the covariance of the cross terms. Okay? Okay. Fifth property, what happens if x and y are independent? Then what is cov of xy? By definition, this is expectation of xy minus expectation of x, expectation of y. But if x and y are independent, expectation of xy is equal to expectation of x, expectation of y, and so this is 0. Okay? So, if x and y are independent, then the covariance is 0. Warning, converse is not true. It is certainly possible for the covariance to be 0 without x and y being independent. Okay? One can construct examples without too much difficulty. Okay, so you should be careful. But a consequence of this is using star, the equation above. So if x1 up to xn are independent random variables, then by star we have that the variance of the sum. So let's look at star. So variance of the sum is this expression, but if the xi's are independent, then this covariance term drops out. Okay, and so you get sum I equal to 1 to n variance of xi. Okay, so let me box this. Okay. So what this means is that we have linearity of variance under the independence assumption, if the random variables are independent. Okay, so this is also something that we will use several times. Okay, so expectation is always linear. So expectation of the sum of xi's is always the sum of the expectations of it. But variance is not in general. But if they are independent, then you get this also. Okay, so this is important. Okay, so are there any questions about these properties? We will use all of this.
So is there any signature in the joint PDF which would indicate that its covariance is positive or negative or 0?
No, no, that's right. No, one has to work through it. Yeah. I mean, you could plot it if there are two variables, and you can try to see where the mass is more, either by both in the continuous and the discrete case. But in general, one would just have to do the computation. Okay, so So the covariance is a good measure of association. It tells you if the covariance is positive, that means things sort of move together, and if it's negative, then they move up in opposite ways. As one increases, the other decreases, like that. Tends to, of course. But it's not a great notion, because so the problem with the covariance the problem with talking while writing with the covariance is that it is unbounded in either direction. Okay, so if I know if covariance of xy is let's say 1000, I know that they are strongly correlated. But what does that mean? I mean, how strongly correlated? I mean, it could go. Why is it not a million? Why is it not a billion? So we can't say for sure. We can't say how strongly correlated. X and Y are. Right? You see, this is the problem. Or if it were minus 1000, then how negatively correlated? How strongly negatively correlated? Like that. So, so a better measure of measuring association, and this is related to what I said at the beginning of the class, is the correlation coefficient. The correlation coefficient of x and y of the random vector xy is rho of xy, usually denoted rho. This is covariance of xy divided by the square root of variance x times variance y. Okay. And why is this a better measure? So of course it has the covariance in it, but it's scaled by something. And the advantage of this is the following theorem. Is that mod of rho of xy is less than equal to 1. Which is equivalently the statement that mod of covariance of xy is upper bounded by the square root of variance of x times variance of y, and this is the essentially the Cauchy-Schwarz. So this is a problem in the book. I will give that in the homework. Okay, so that that you can see, and equality occurs if y is a linear function of x. So ax plus b with rho equal to 1 if and only if a is positive, and rho equal to minus 1 if and only if a is negative. So in other words, if a goes in the same direction as x, then you get rho 1, and if a goes in the opposite direction, then you get rho as minus 1. Okay. So therefore now you can say, I mean, if your correlation coefficient is 0.9, that means it seems to be very strongly correlated, whereas 0.1 may be not so correlated. Okay. And this is why we talked about the sample correlation coefficient, and we defined it in a very similar way. So you see, this thing is like the covariance, and this is the these are the standard deviations. I think there should have been a square root here. Okay, I'll double check. Yeah, because I think there should have been the standard deviations. Yeah, right, because S squared was the sample variance, so these should have been squared over here. And so these are standard deviations, and which is precisely square root of variance. Okay, so these come from data, and this come from random variables, but they are very closely related, as we will start to see. Okay, there was one thing I forgot to say at the beginning of the class, which I so aside. So I'll say this quickly. I'm running over time. So I just want to make this remark. Maybe I mean it's kind of obvious, but it's just to reinforce this idea, this point that marginals do not determine the joint distributions. So if I know the marginal distribution of x and y, I do not necessarily know the joint distribution of x and y. And here is an example to illustrate this point. So I take two cases. So suppose x and y are uniform in 0, 1 squares. That means they are jointly continuous, and their joint PDF is 1 in this square. Right? It's exactly 1. So when you integrate it, you get 1. And the second one is x and y uniform on the diagonal x equal to y in 0, 1 square. Sorry. So draw it with a different color. As usual. Okay, whatever. So in both cases, x and y are uniform 0, 1 random variables. But their joint distributions are very different. In one case, it's uniform in this entire square. In one case, it only lives on this diagonal. Okay, so this is something that you should keep in mind. I mean, just because you know the marginals does not tell you the full distribution. Okay, so yeah, sorry for going over time. I'll stop. Are there any questions? I think I've answered everything. Yeah, so this kind of inequality is, this Cauchy-Schwarz again tells you that this curve is like an inner curve. Okay, so let me stop recording.